All right, welcome to The Explainer. Today, we're going to tackle a huge headache in modern statistics, that feeling when your models are just grinding to a halt. And we're going to uncover a really elegant solution that comes straight from the world of physics. You know, if you've ever used a standard MCMC sampler, I'm sure this looks painfully familiar. You're staring at a trace plot, and the sampler is just stuck. It's exploring this tiny little area, moving at an agonizingly slow pace. It honestly looks less like a methodical search and more like, well, a drunkard's walk. And look, this isn't just annoying, it's a total deal breaker. When your model has, say, 50 or 100 parameters, this whole random walk approach just completely falls apart. The search space is so unbelievably massive that just guessing is never going to work. So what's really going on here? Well, it's something called the curse of dimensionality. As you keep adding more and more parameters, the part of the space where all the good stuff is, the typical set, becomes like the thin skin of an orange. Almost all the volume is in that tiny shell, but it's floating in this gigantic empty space. Trying to hit it with a random step is like trying to hit that skin with a dart from across the room. You're almost guaranteed to miss, and you're just burning cycles for nothing. Okay, so if random stumbles are basically doomed from the start, we need a better plan. We have to stop guessing and start exploring with some intelligence. And that smarter approach comes from this really cool and powerful idea from classical mechanics. The solution is to think about our statistics problem like it's a physical system. And the method that does this is called Hamiltonian Monte Carlo, or HMC for short. So let's just throw that whole drunkard's walk idea out the window. Instead, I want you to picture a frictionless puck just gliding effortlessly across some kind of landscape. This puck isn't just wandering randomly, it has momentum, and it follows a path that's dictated by the shape of the surface itself. But how does this puck know where to go, right? That's the key. HMC uses the gradient, you can think of it as the literal slope of the probability landscape at any point, to guide its movement. It just naturally glides toward the areas of highest probability, making these long, efficient leaps across the parameter space, instead of those tiny, useless random steps. I mean, this comparison says it all, doesn't it? A standard sampler is like someone just fumbling around in the dark, hoping they bump into something good. HMC, on the other hand, is like a satellite locked in orbit. It's using the force of gravity, which is our gradient, to stay on this perfect, efficient path that explores huge distances with every single pass. We're going from stumbling to orbiting. Okay, so how does this actually work? How do we take a statistical distribution and turn it into a physics simulation? Let's pop the hood and see what's going on. It's a pretty beautiful combination of ideas. So it's basically a three-step dance. First, we set up the landscape. We treat our probability distribution as a potential energy surface, where the spots with high probability are like deep valleys. Second, we introduce kinetic energy. We give our little puck a random push, some momentum, so it can actually roll across the landscape. And finally, we use this clever simulation trick called the leapfrog integrator to map out its path, updating its momentum, then position, then momentum, over and over. So what's the secret sauce here? Why is simulating physics so much more powerful than just taking random steps? What's the real magic that makes this all click? And the magic, it really comes down to one thing: energy conservation. You see, in a perfect physical system, the total energy, that's potential plus kinetic, is always constant. And because our HMC sampler is following these physical laws, the new places it proposes to go are almost always valid points from the distribution. This means you get an acceptance rate that's close to 100%. Now compare that to a random walk sampler that might throw away most of its proposals. You can see why this is such a game changer. Okay, so this isn't just some cool theory, right? This is the high-performance engine that's inside the most powerful statistical software we have today. There's a reason this physics-based approach is the industry standard. In fact, modern tools like STAN and PyMC take this even further. They use an algorithm called the no U-turn sampler, or NUTS. You can think of it as a smart GPS for our puck. It automatically figures out how long the simulation should run, letting the puck roll just long enough to find new territory, but stopping it before it wastes time making a U-turn and coming all the way back. It makes the power of HMC super robust and way easier to use. So here's the bottom line. You don't have to build the rocket yourself, but you really do need to know how the fuel works. By understanding the basic physics behind how these samplers operate, you can build way more sophisticated models, you can figure out what's wrong when things break, and you can trust that your sampler is actually exploring the whole universe of possibilities. It's about knowing why the engine is so powerful so you can really put it to work. So the next time you build a model, ask yourself, are you going to let it stumble or are you going to let it orbit?